Hello, everyone. My name is Matthew Finger. I'm a senior in electrical engineering at Weber State University, and I've been given the honor to talk to you all today about our open source antenna pattern measurement system and the software-defined radio-based student research and development that has gone into it. So I will break this presentation down into 4 parts. We've got the background, the different phases that it's gone through, the application. I'll show 3 different antennas that we've tested with our system, the upgrades that the system has gone in recent years, and then finally some future work and summary of the entire project. So the background of the projects all started in 2011. There was an article written in the IEEE Antenna and Propagation magazine about 2 students that graduate students from the University of Illinois that created a antenna pattern measurement system using 2 of the old Linksys routers. And they used the Linksys routers uploaded with open source DDR-WRT software, where the routers would handshake and then measure the signal strength of the antenna under test. And then the router would rotate and do the same thing until it had the full 360 degrees of its azimuth measured and then patterned out. And so one of the professors, Dr. Hearn at our university, saw this and wanted to recreate it in one of our labs. And once the entire project was recreated, we wanted to update it to kind of today's standards. We wanted to replace the Linksys routers with software-defined radios, the motor controller with an Arduino, and use symmetric belts and 3D printed materials to make it all more accessible and portable. And so Weber State University wrote to the Utah NASA Space Grant and was given a grant to kind of move this project along into the next generation. And we wanted to use it for kind of outreach and loan opportunities with other universities. So this was in phase 1 in 2018. We had a master's student named Dan Newton create this first system where we have a directional antenna pointed downrange at our antenna under test. And the antenna under test would measure the noise, the ambient noise, and then we would send a band-limited noise through the directional antenna, measure it from our antenna under test, take the average of from the time, and compare it to FECO simulations. And we have the top here, a monopole antenna, and the bottom, a patch antenna, to have different kind of antennas to show the measurement of our noise cancellation system versus our simulated system. And then from there, we had a second master's student pick up the project, and he wanted to incorporate coherent AM detection as opposed to measuring the ambient noise and then measuring the signal. And he wanted to just do it all at the same time. And the key takeaway is to achieve that coherent detection, we needed to tie the clocks of the transmitting software-defined radio and the receiving radio together. We used 2 hack RFs, and since our software-defined radios are in close proximity, we were able to tie their clocks together physically, and that way we didn't have to search for a software solution to that. And then we used an Arduino Uno programmed with the G code to use our stepper motors to rotate on the azimuth. And it's all controlled through a laptop. And we did a simulation in Multisim here to show the concept of our coherent AM detection. The big takeaway here with this graph is the top is our input, the bottom is our output, and the modulator and demodulator are tied together in a common source, effectively tying their clocks together. So in 2021, we wrote to the Utah NASA Space Grant and received additional funds to continue our project. And we had a mechanical engineer step up and redesign the masthead using all 3D printed materials, kind of going with our direction of having it more portable. And as we can see, the masthead all comes apart and fits nicely in that suitcase. And we also were testing out in various lab rooms and parking lots and things like that to show the measurements were similar regardless of the kind of noisy environment, and it didn't need an anechoic chamber to get close to our validation simulations. So we'll move on to the second part. I'm going to show just a couple of antennas that we've tested with it. The first was the microstrip patch we have up in the top there. That is the actual physical microstrip patch picture. They have the FECO simulation of it, and then we have our FECO simulation versus measured in a noisy environment. And again, the patch a lot of times is seen in GPS and space communications. This one doesn't have a ground plane, and that's why we have a kind of a reflection of our main lobe down below. The second was the quarter wave monopole. It's the kind of iconic butterfly wings of the antennas, and it's mostly seen in handheld radios. And once again, we have the pictures of the actual physical quarter wave monopole antenna we made, the simulation, and the results. And then finally, we have our Endfire Array Yagi prototype, which was built and simulated. And this is to test the directionality to make sure that we have kind of the GPS antenna, the handheld radio antenna, and the directional antenna. This was used a lot in kind of television back in the day. So that's where I came into the project. A lot of the software was from before 2018, and it needed to be up to date because we wanted to port it over to a Raspberry Pi. And Raspberry Pis use a Raspberry Pi operating system named Raspbian, which is essentially a Debian offshoot. And so we wanted to update the Linux operating system to that Debian version, update the Python protocols and the Python code, and then update the GNU Radio companion block flow diagram. One thing with each kind of step is to show that it is kind of able to go into the forward through generation of code. It all can be made so that if there is a update that requires different syntax, for example, that a student would be able to go in and change the code and update it so that a single update isn't going to effectively destroy or cause the entire system to stop working. So with the GNU Radio flow graphs here, we had our transmitter model going into a multiplier, and then our Osmocom sync, which is the sync required for the HackRF. One thing that is nice is that once you've compiled your GNU Radio code into the Python and you have kind of modeled that as a Python class, you're able to take any of the variables in there and reassign them. So for example, in our system, we have the frequency of our modulator as a user input. So therefore we can take multiple frequency measurements. So go from 2.4 measurement, 2.41, 2.42 to see the frequency response kind of over a broader range. And then here is our receiver model. Again, once coming in from our Osmocom source into our multiply, upgrading from the later levels to the current version of the GNU Radio. One thing that we noticed was added was the windowing on the kind of low pass filters, but everything in the Python code defaults, luckily. So if you did not go back and recreate a flow graph at a later time, it would just default. It would have a default value associated with it. So I think the kind of, for example, was the windowing was a Hamming window, and we changed it to a Kaiser because we got slightly better results with that. And then so once all the software was up to date, we took new measurements across a laptop, and we made sure that the code was both 64 and 32-bit compatible, and it made multiple backups here. So we have, once again, our monopole, or our butterfly wings on the left, and our patch antenna on the right. And that brings us to the next step of the project, was to get the entire system to be running on a Raspberry Pi. And the main draw for the Raspberry Pi was the SD card. Once you've set it up once, you're able to create an image of that SD card and then flash that SD card as many times as you want. And all you'd have to do is plug that SD card into the Raspberry Pi to get the full system up and running, as opposed to getting a laptop, installing Linux, making sure everything, all the dependencies are up to date, Python, GNU Radio, again, update the dependencies. And so we just wanted to streamline the process a lot more. One thing that was of concern, though, was the USB ports. We used 2 HackRFs and the Arduino controller. Right, there's 3 USB ports. That's not counting a keyboard and mouse. And we didn't want to connect to a hub because that could potentially add more noise to the system. So we would eventually transition into a touch screen with the keyboard in the 4th USB to avoid that. So our first attempt was with a Raspberry Pi 3. It was more readily available, especially with supply issues nowadays. So we got it a lot earlier than the Pi 4. However, we noticed that the measurements that we acquired under the Pi 3 were extremely noisy. as we have the monopole once again on the left and the patch on the right, and you can see how kind of jarring all of the different measurements are from each other when they should be kind of a smooth curve. And we were also getting memory errors. A DRI2 failed to authenticate, where 1 in 10 times of running the program, it would effectively crash, and there would be no way to track down which part of the memory was crashing specifically unless you hard rebooted the Pi. And so between the kind of data acquisition and the errors crashing the program, we unfortunately did not continue with the Raspberry Pi 3, but we had a Raspberry Pi 4 already ordered, and when that had come in, we had redone the measurements with the Raspberry Pi 4, and we see the comparison between the two. The Raspberry Pi 3 is once again in the blue, and the Raspberry Pi 4 is in the orange, and it fixed the issues that we were having with that very jarring and noisy hardware, as well as the memory issues that were occurring. One thing with this test is we wanted to make sure all of the variables were as consistent as possible. So we made sure that it was the same exact antenna that was used, the same location, the same distance from our transmitter to our receiver, and we went as far as using the same SD card between the Raspberry Pi 3 and 4, where we would run the transmission or the test as under the Raspberry Pi 3. We would take the SD card out, unplug the USB ports, plug all of everything in the Raspberry Pi 4, plug the same SD card back in, and rerun the program. And the kind of results, I guess, show for themselves there of how much better the data acquisition is for the Raspberry Pi 4 versus the 3. Next, we had the directional antenna. We noticed one problem when going from the legacy code to the newer code was that effectively the more directional antennas were causing large side lobes that we couldn't explain at first. But when we looked into the data, everything along the main lobe of that first one was exactly the same. And since we're normalizing around the directionality or the maximum signal strength, it effectively caused these side lobes to become much larger than what they should have been. We went through and tried to change a bunch of receiver settings to see why we were effectively cutting off data, or that we'd peaked, or one of the two. And it wasn't until we tried messing with the transmitter gain that we noticed that when we turned the transmitter gain down in the newer code as opposed to the older code, that we would get the directional antenna measurement that we were expected there in the orange, as it has the kind of full main lobe, and the side lobes are much better down to proportion, as they should be. So that brings us to the future works of the project. One thing that we want to incorporate, like the second half of my senior project, is to get a 3D, go from a 2D measurement to a 3D measurement. We have kind of a new base that's underway to get the elevation control. As of right now, we only have that azimuth control. And once we have that elevation control, we'll be able to take our antennas and map them in a three-dimensional plane. And then there's also mechanical improvements, sensors, and we have, this is just kind of a list of other things that can be added on to the project. And I'm sure there's many, many, many more that people can think of as time goes on. So this brings us to the summary. We wanted to really emphasize that it is an open source, it's student maintained. A lot of antenna measurement systems require a professional license and have a professional team come and set it up. And if there's an update that causes something to crash or a sensor to not work, you have to then pay that professional team to come again and work on your antenna measurement system to get it back up and running. And sometimes they can't even get it back up and running and have to replace the entire thing. So this entire program is student maintained. Again, it uses Linux, GNU Radio Companion, Python, Arduino, 3D printed materials. It is all something that you could give a student or even someone just in the amateur radio field, and they would be able to kind of work on it and fit it to their needs. It also shows that this, just reiterating one more time that open source, it's gone from a 2018 version to now a 2022 version. So we've updated software already on it, we've updated hardware, and to show that the process will kind of grow along with time as 3D printed materials become better, or the software, because I know the GNU Radio has 4.0, so I'm looking forward to diving into that as well, and to update that. And then all the measurements were done kind of in a noisy environment, and we'll eventually be doing them kind of in an anechoic environment to compare the two. Some acknowledgements. We'd like to thank the Utah NASA Space Grant for sponsoring us to get it all started and kind of got us to where we are today. Moog Industries donate a lot of the absorbers that we use in our tests. And then Weber State University, we had Dan Newton and Taylor Hansen, the two electrical engineer master students that worked on it before me. And Ren Fisher was the mechanical engineer that worked on the 3D modeling of the new base mast. And then Christian Hearn and Justin Knighton were the two professors that have kind of advised us along the way and helped us kind of bring everything together. Was there any questions?
All right. So we can maybe take one question while our next speaker, Chris, can move towards the podium. Are there any questions? Where's our next speaker? Chris? Oh, there we are. Okay. Yeah. Okay. Actually, so while he's walking up, I have a question. Do you have any theories where that noise came from in like the Raspberry Pi 3 measurement?
On the Raspberry Pi 3s, we read a lot about how people were getting essentially popping in noise depending on when they listen to audio, depending on the USB ports. And so our main theory was going to be testing the USB ports as to kind of isolate that noise down. But when the Raspberry Pi 4 came in and we saw that it had effectively eliminated that, we didn't want to do extensive testing on something that was effectively out of date.
All right. Well, thank you very much, and a big round of applause.
Thank you.